Hello, welcome to EEE 41, Lecture 1, Semiconductor Fundamentals. So for this lecture, we'll cover general material properties of semiconductors, including identifying common semiconductor materials. We'll discuss semiconductor crystal structure and introduce the crystallographic notation or Miller indices. We'll also discuss the concept of electrons or free electrons and holes in this lecture. Hopefully, by the end of this lecture, we'll be able to do the following or meet the following objectives. First, to visualize bonds between atoms in a silicon crystal in terms of its lattice structure or its actual 3D formation of atoms within the crystal, and bonding diagrams. So bonding diagrams, on the other hand, is a simpler 2D representation, which is a useful tool or visualization tool in um, analyzing the interaction of atoms and electrons in our semiconductor materials. So next objective is to perform basic computations for a given crystal structure and dimension, such as the density of atoms or the density of valence electrons. So there's just a simple example in this lecture. More detailed examples can be found in the problem-solving slides. 3. Describe what a semiconductor's intrinsic carrier concentration represent. And lastly, identify the conditions for thermal equilibrium. Before we analyze semiconductors, we clear up first what is a semiconductor. We can start with something more familiar, which are conductors and insulators. So conductors have low resistivity or high conductivity because they are just reciprocals, while insulators have high resistivity. We then put semiconductors in the middle and say that semiconductors are those with intermediate resistivity between insulators and semiconductors. A large part of semiconductors in ICs or integrated circuits are crystalline in structure, where atoms follow an ordered pattern across the whole material or over a wide scope. So that one is shown in the figure on the right. However, non-crystalline semiconductors also play a role in recent and emerging technologies. Amorphous semiconductors do not follow a pattern over a long range or scope. Somewhere in the middle is polycrystalline structures where portions of different sizes and orientations follow locally the crystalline pattern. Common semiconductor materials are highlighted in the table. The base material for a semiconductor device may be elemental or composed of a single element such as pure silicon, pure germanium, or pure carbon. A base semiconductor material may also be a compound. For compound semiconductors include silicon carbide and germanium silicide. Aside from 4,4 compounds, we also have 3,5 compound semiconductors, which include germanium arsenide and indium phosphide. 2,6 compound semiconductors include cadmium sulfide and zinc telluride. Aside from elemental and compound semiconductors, alloys can also be used as a base semiconductor material. If you may have noticed the pattern, elemental semiconductors belong to group 4, while compound and alloy semiconductors have group numbers that sum to 8, which makes each atom, quote-unquote atom, effectively have 4 valence electrons. For a 3,5 compound, the group 3 element can borrow 1 electron from the group 5 atom, then both would have 4 effectively. However, among these, silicon is currently the most common because of its abundance. It can be obtained from sand, and also its usability around room temperature and ease of fabrication and processing. In isolated atoms, such as the one shown in the figure, electrons occupy the lowest stable energy levels available. The energy levels, as indicated in electron configurations as 1s, 2s, 2p, 3s, 3p, etc., are discrete and have a limited number of electrons that can occupy each energy level, which we refer to as the state. As depicted in the picture, the fixed positions where the energy levels lie relate to the fixed stable energy levels, where those levels or energy levels closer to the core of the atom have lower energy, while those at farther from the core of the atom have higher energies. For the case of an isolated silicon atom with 14 electrons, 10 electrons fully occupy the 1s, 2s, and 2p energy levels. These electrons are referred to as the core electrons and do not actively play a role in carrying currents in semiconductors. The remaining 4 electrons lying in the 3s and 3p energy levels are called the valence electrons and will be of our interest for this course. So we have here the 4 valence electrons, which are the ones involved in forming covalent bonds with the neighboring silicon atoms to form the silicon crystal. So this depiction of the silicon atom is only applicable when it is isolated and not when the atoms form our crystals. What then happens when we go from separate silicon atoms to a silicon crystal? Silicon atoms form covalent bonds to four nearest neighbors, where each covalent bond represents a shared atom. So in this figure in the middle, a dashed line represents one covalent bond. With the sharing of electrons, the 8 valence electrons per atom is completed. We use what we call a bonding diagram to easily illustrate the bonding between atoms in a 2D manner. However, the actual structure of the silicon crystal in 3D is the one shown in the right. The fancy image we have just shown is what we call a unit cell for the silicon crystal. In general, a unit cell is a small portion of the crystal that can be repeated to reproduce a larger crystal. Shown with green atoms is called the simple cubic unit cell. There are other unit cell types such as the face-centered cubic or the FCC, the body-centered cubic BCC, and a lot more which include non-cubic unit cells. Visually, we can say that the unit cell for silicon is not among the three shown in the figure. So what is the unit cell for the silicon? The unit cell for silicon is called the diamond lattice structure. It is a cubic unit cell and thus have the same length for all edges, which is called the lattice constant and denoted by the letter A. So here we have the same length for each edge. The lattice constant, or A, for silicon at room temperature, okay, is, or 300 kelvins, is 5.43 angstroms, where 1 angstrom is equivalent to 10 raised to minus 8 centimeters. We also note that each silicon atom forms a tetrahedral structure occupying a smaller cube with its 4 nearest neighbors. However, this smaller structure cannot be considered as a unit cell of the silicon crystal as it will not produce the crystal structure when repeated. We also note that the crystal will look differently when viewed from different directions as shown in the right. So this influences how electrons and atoms interact within the crystal. So the diamond lattice structure actually looks very complex. To help us visualize it, we can dissect the unit cell as composed of 8 corner atoms, 6 face atoms, and 4 atoms completely inside. For the 8 corner atoms, only 1/8 of the atoms are inside the cube, while for the 6 face atoms, only 1/2 of the atoms are actually inside the cube. So the 4 atoms completely inside are, of course, completely 100% inside the unit cell. The location of these atoms are at 1/4 of the body diagonal. So let's just be clear, the body diagonal is from one corner to another opposite corner, and when we draw a line to those corners, the length will be square root of 3 times a. So you can use your geometry to prove that, and each of these red atoms are placed at 1/4 of the body diagonal. So from corner to another corner, the distance, or sorry, from the corner to the atom inside, the distance is 1/4 square root of 3a. So what if we were asked how many silicon atoms are there in 1 cubic centimeter, or what is the volume atomic density of the silicon crystal? We can start computing using only the unit cell. So if we count the atoms inside the unit cell, we know that we have 4 atoms completely inside. We have 8 corner atoms, but these are shared among neighboring unit cells. Each corner atom is only contributes 1/8 to a unit cell. So the 8 corner atoms is only equivalent to 1 atom inside the unit cell of concern. We also have 6 face atoms shared by 2 cells each, or each face atom only contributes 50% of an atom. So the 6 face atoms is just equivalent to 3 atoms inside. So in total, we have 8 silicon atoms per unit cell of the silicon crystal. And so we proceed by computing first the volume of the unit cell. Since it is cubic, the volume is a cubed, and we'll get 1.6 times 10 to the minus 22 cubic centimeter. The number of silicon atoms per cubic centimeter would then be 8 over a cubed, or 8 over the volume of the cell, which gives us 5 times 10 to the 22 atoms per cubic centimeter at room temperature. Note that this density will change at different temperatures because the unit cell lattice constant, or sorry, the lattice constant will change depending on the temperature. So this density of atoms is important, and we'll go back to this as we go along the course. Aside from silicon, germanium, which is also a common semiconductor material, follows the diamond crystal lattice structure. However, for compound semiconductors, a majority of these materials follow what we call the zinc blende lattice structure, which position-wise is very similar to our diamond crystal lattice. But since there are 2 different atoms in the crystal, the placement of the atoms is shown in the figure. So some compound semiconductors that follow the zinc blende lattice structure is gallium arsenide, indium phosphide, and silicon germanium. However, not all compound semiconductors follow the zinc blende lattice structure. Some compound semiconductors follow a Wurtzite lattice structure, which we'll not cover in this course. So in discussing crystalline materials, we actually have what we call the Miller indices, or a crystallographic notation to help indicate or specify which direction or plane we are referring to. So we have three numbers to represent the x, y, and z directions. So the directions as shown in this table is denoted with square brackets. And if we want to denote this highlighted plane on the left, then this must be along the crystal plane 0, 0, 1. So there are rules governing how we write this. If you're interested, you can read the book. But for now, we'll just give you um, diagrams with Miller index notations to help you visualize certain problems. Another thing that you may have noticed is that crystalline or crystal planes of the same numbers or having the same indices are actually normal or perpendicular to that to its corresponding direction. We also have equivalent planes and equivalent directions since crystals have repeating patterns. So this 001 say plane here is also equivalent to this plane at the bottom. And this direction 001 here is also the same as the direction 001 here. So with the help of the Miller indices, we can actually identify the direction at which we want to look at our silicon crystal. So for example, we would want to view it from, say, direction 100. So let's say this is the z axis, this is the y axis, and this is the x-axis. If we would want to view it from 110, then we'll look at it from this point of view, and this will be normal to our view, and therefore we'll get this view from the direction 100. If we view it from 110, so this is actually right straight into this edge right here. So this edge right here is this one. And so we'll get this seemingly different view of the crystal. We can also view it from 111, which is straight through this corner. So this corner atom here is actually this atom in the middle. And what can we say about this? The material properties actually change with orientation and direction. So when we say fabricate or analyze crystalline semiconductors, it is actually necessary to be very specific with the direction. And as such, silicon wafers where our integrated circuits are made are usually cut along the 100 plane with a flat or notch to orient the wafer. This is to help those that transport, those that handle the silicon while it is being processed to orient it in the proper manner. And also, most of the processing happens from the top surface, or the chemical reactions happen with the top surface, and so having this notch right here actually specifies that the surface of the silicon or of the wafer is actually along the 100 direction. Okay, so although the 3D drawing of the crystal gives us a lot of insight, there are actually some things that we can say analyze or imagine simply with 2D models or our bonding diagram. So we'll use the visualization of electrons and holes using this bonding diagram. So again, in this representation, covalent bonds or shared valence electrons are represented by solid lines. And here we can see the silicon atom core. So these black lines are actually our valence electrons. However, with enough energy, these electrons can break loose and break the covalent bond. So what will happen visually is that the bond will be broken, and therefore we'll have what we call a free electron or conduction electron. Now, the missing bond um, is what we call the hole. Sometimes we represent that with a missing line, a dashed line, or a circle. So note that the free electron and the hole in this manner are always created in pairs. When the covalent bond is broken, you will always have one new free electron and one new hole. However, the process can also be reversed. The free electron can also occupy the missing bond or hole, and therefore the electron hole pair will be annihilated. Okay, next, mobile charge carriers. So the free electrons and holes are what we call mobile charge carriers. So they are the ones used to carry current and the ones that affect the resistivity or directly affect the resistivity of our material. So to carry current, you have, of course, some charge, and also you should be able to freely move around the material. So unlike the covalent bonds, which are bound within the crystal, um, these electrons in the covalent bonds are not considered carriers. So for our carriers, the free electrons are negatively charged, where holes where there are actually missing electrons are considered positively charged. So if you look at this GIF here, the holes move in a different manner compared to free electrons. Why is that so? Because free electrons can actually move freely around the semiconductor crystal, whereas holes, being the absence of electrons, are only limited to where the original covalent electrons should be. So that one is depicted by the blue lines shifting from one direction to another. So before we start doing some math, we'll define some of our variables first. So N, we'll use the letter N to denote the number of free electrons per cubic centimeter. So this is some number per volume. P will be the number of holes per cubic centimeter, and we'll use N sub I to represent the intrinsic carrier concentration. So for all these three, the units will be a number per cm cube, but most of the time will not indicate anymore the number and just use cm raised to minus 3 or per cubic centimeter. So what exactly is this intrinsic carrier concentration? So say we have a pure semiconductor at equilibrium. If we let it be and let the randomness kick in, so some electrons will have will have enough energy to break a covalent bond. At random, some will form new covalent bonds. So the average effective number of electrons or holes per cubic um, per cubic centimeter, that number will be the Ni, and that is unique to the material for, or a characteristic of the material at a specific temperature. So since free electrons and holes are created or annihilated at the same time, then therefore with our pure semiconductors, N and P will always be equal to each other. And if we let it reach equilibrium, then that will be N sub I, or the intrinsic carrier concentration. Something to remember when we say EHP, uh, we mean electron hole pair. So what do we mean when we say equilibrium or thermal equilibrium? It is a state, a steady state where no external forces are applied. So there is no electric field that is applied to the material. There is no magnetic field. There is no mechanical stress. The material is not being compressed or elongated. There is also no light. If you leave that material and let it reach some steady state, then the material is said to be in thermal equilibrium. So this is a dynamic situation in which every process is balanced by its inverse process. So the electron hole pair generation is actually equal to the um, recombination rate, meaning in average, the number of electrons or the concentration of free electrons and holes in the material effectively does not change, although it does not mean that they do not exist. So the generation rate and the recombination rate can actually cancel out. So that would only mean that no new electron hole pairs are generated, but there are actually some electron hole pairs in the material. Aside from the balancing of the generation and recombination, we can also say that drift and diffusion are actually balanced. However, we'll talk about this um, in future lectures. So what is the intrinsic carrier concentration of pure silicon? So we recall that, or we say that covalence bonds are actually weak enough such that some of the bonds will break at any temperature greater than 0 Kelvin, such that at room temperature, actually a considerable number of these bonds are actually broken. So in this figure here, you can see that Ni, which is the y-axis, and temperature, which is the x-axis. This plot shows that the intrinsic carrier concentration increases with temperature. It is only expected because as you increase the temperature, the thermal energy increases, and therefore it is more likely that electrons will have enough energy to break covalent bonds. Specifically for silicon at room temperature, the intrinsic carrier concentration is approximately 10 raised to 10. So that's a very good number. You'll have to remember that, and we'll use that um, very often in this course. However, note that that value is only valid for room temperature. You'll actually need to say look up or look back into this plot, or use some models, or use a different or the Ni might actually be given in cases where um, the temperature is not 300 kelvins. Also, note that different materials will have different intrinsic carrier concentration even at the same temperature. So we'll know later on what material properties actually affect this intrinsic carrier concentration. So in summary, we have actually discussed the crystalline structure of silicon, which is important for a majority or a large part of semiconductor devices. Silicon have 4 valence electrons per atom. Each silicon atom bonds to 4 nearest neighbor atoms and follows a diamond lattice structure. The volume atomic density of silicon is 5 times 10 to the 22 at room temperature. The intrinsic carrier concentration is 10 raised to 10 at room temperature. So actually comparing this number, um, you we should be able to say appreciate that even if there are covalent bonds that are broken in average for our silicon crystal, it still mostly remains intact in its crystalline structure. So 10 raised to 10 is just a very small percentage of 5 times 10 to the 22 atoms within your crystal. Also, we have identified mobile charge carriers, or simply denoted as carriers, which are produced in pairs when covalent bonds break. So we have our free electrons, which are negatively charged, and holes, which can be considered as positively charged mobile particles. So the core electrons and valence electrons in covalent bonds are not considered carriers, as they cannot help or cannot conduct current. Okay, so that's the end for lecture 1. Please follow the problem solving slides that follow. Thank you very much.